Okay, so today we are going to go over the review. This is probably going to have to be shot over quite a few little videos, and that will be fine. Let's start with fill in the blanks. We're going to start with first blank, a horizontal line where the y values of the graph rational function approaches as the x values approach negative infinity and positive infinity. This is what we call a horizontal asymptote. Okay, so first you will find the horizontal asymptote, you first find the numerator and the denominator. If the degrees of the numerator and the denominator are the same, you find it by dividing the leading coefficient. So in the case of our first example, I'm going to zoom this in. Still a little more. Okay, in the case of our first example, you observe that the numerator is a second-degree polynomial and the denominator is a second-degree polynomial, which means we now look at the leading coefficients. The numerator has a leading coefficient of 2. The denominator has a leading coefficient of 1, and it's one that you do not see right away. And so your horizontal asymptote is simply 2 over 1, which is just 2. Okay, now let's turn our attention to number 2. Here, both our numerator and denominators are third-degree polynomials, but unlike the previous example, your leading coefficient on the numerator is 1 and the denominator is 3. So your horizontal asymptote is merely y is equal to 1 over 3. Okay, now if the degree of the denominator is greater, regardless of the coefficient, then y is equal to 0, as we see in these two examples. Here you have a first degree over a second, horizontal asymptote is 0. Here you have a second over a third. Again, horizontal asymptote is 0. These things must be remembered as a matter of fact. The next thing that you run into is a hole, is a break in the graph of the rational function that occurs when the values of x makes the numerator and the denominator equal to 0. Simply put, it cancels out. So if we can cancel it, we can remove it, and so we will call that a removable discontinuity. And then, of course, the last blank is talking about where the denominator is equal to 0. That is, of course, a vertical asymptote. Now, below on the review, there is a number of examples that we need to work through in order to get this correctly. So I'm going to zoom back in so we can see number 3 in greater detail. Okay, so number 3. It's asking you to find the removable discontinuity and the vertical asymptote. Well, the first thing you always do is to factor. So here I have 3x plus 9, and I have x squared plus x minus 6. Well, I first look at my numerator and I recognize, okay, 3x and 9 are both multiples of 3. So this is very simply 3 times x plus 9 divided by 3 is 3. And so now I have the numerator in factored form. I do the same with the denominator. The denominator is a little bit more interesting. I know that this is going to be x and x, and so I am looking for the factors of negative 6 that have a difference of 1. I know one of these is going to be positive and one of them is going to be negative. This is 3 minus, this is going to be 3 minus 2, because 3 minus 2 is equal to positive 1. Excuse me. Whereas 2 minus 3 is equal to negative 1. So, now that I have it in factored form, I need to find the zeros of the denominator. Well, The zeros of the denominator is where I pull each factor and set it equal to 0. Now, by subtracting 3 from each side, I have that x is equal to negative 3. Or if I just remember that insiders lie and that the 0 is the negative of the term inside the parentheses, it is fine. Same here, x minus 2 is equal to 0, and so you add 2 to both sides, and x is equal to positive 2. Now, once we've found the zeros, you can determine which is a removable discontinuity and which is an asymptote, because this cancels with this. That tells me that x is equal to negative 3 is my removable discontinuity, and that x is equal to positive 2 is my asymptote. And that's all there is to that one. Number 4 is, shall we say, a little bit more interesting because there's factoring to be had all over the place. So, we look for the factors of 15 that add up to 8. Well, the factors of 15 are 5 and 3, and they are both positive because this is positive and this is positive. Now, on the bottom, you are looking for the factors of 8 that add up to negative 6. Now, since 8 is positive, we know that they have the same sign, and we know that both of those signs are negative from the constant, or from the coefficient negative 6. So we actually have negative 4 and negative 2. Here we know that there are going to be 2 vertical asymptotes, and you notice there is nothing in the numerator which cancels anything with the denominator. So the removable discontinuities, there are none. And instead, you have 2 asymptotes, one where x is equal to 2, and the other is where x is equal to 4. Now the third one is a little bit different. You recognize that the numerator is actually 3 times x squared minus 9. Well, x squared minus 9 is a difference of squares, and that is then 3 times x plus 3 and 3 times nx minus 3. We only have one 3, so don't worry about that. 3 is the leading coefficient, which tells you the horizontal asymptote but doesn't tell you the vertical. Now in the vertical we need to factor the denominator. We are looking for the factors of negative 18 that have a difference of 3. And so you know it's going to be x, and you know that it is going to be plus and minus, and it is going to be 6 minus 3, not 3 minus 6, because the 3 is positive. Now that we see that, we need to find the zeros of our denominator. Of course, we remember that insiders lie, so we have x is equal to negative 6 and x is equal to positive 3. But we observe that these two cancel, which means this is a removable discontinuity. So we have a removable discontinuity at x is equal to 3 and a vertical asymptote at x is equal to negative 6. Now, let's take a look at the rational functions. To do that, I may have to zoom out a little bit, but that's okay. So for numbers 6 and 7, they gave you the, and there was a little bit of a typo, they gave you the parent function f of x is equal to 1 over x, or you might think of this as y is equal to 1 over x. I don't know why the y didn't show up, but that's okay. They're asking you for the domain, the horizontal, and the vertical asymptotes. Now, the easiest way to do this is to find the asymptotes first, and just remember that where the asymptote is, the set is not. So, let us start actually with the vertical asymptote. The vertical asymptote of the rational parent function is right here where x is equal to 0. You will also have a horizontal asymptote on the x-axis, which is where y is equal to 0. So you go on ahead and you find those first. So I'm just going to say that my vertical asymptote is where x is equal to 0, and my horizontal asymptote is where y is equal to 0. Now, where the asymptote is, the set is not. So let's start with the domain. Our domain is our set of x such that x is a real number and x does not equal 0. Now, while you may not have to replicate this notation yourself, you must be familiar with it because it will appear on the test. For your range, you are dealing with the set of y. Y is also a real number, or the set of real numbers such that y does not equal 0. And that is the original setup for the domain and range of the parent function. Now you look at the transformation of the parent function. Now, the transformation of the parent function is simply to remember that insiders lie, and insider precipitates the horizontal shift. So let's take a look at number 8. If I look at number 8, I have a -2. Now, one would think that this means you are going 2 to the left, but you have to remember that your x is going to lie to you. This is why we don't get along with our x. You think you would go 2 to the right, but instead, or 2 to the left, but instead you go 2 to the right. So you would say this is a shift 2 units to the right. Now, that tells you that your vertical asymptote is that x is equal to 2, and where your asymptote is, your domain is not. So you say that your domain is x does not equal 2. Your range has not changed, and so your range is still that y does not equal 0. Number 9 is very similar, but instead of going 2 units to the left, you go 2 units to the right, you go 2 units to the left. So instead of your domain not equaling positive 2, you will not equal negative 2. The range should still be the same because you have not had a vertical shift. Okay, the next one, as you can see, nothing is lying with your x. Let's keep it that way. But you have a vertical shift of 2. Now, the 2 is outside the fraction, and so the 2 is honest. So we say 2 units up. Your domain then returns to the domain given to you originally, that x does not equal 0. So your domain is that x does not equal 0 because, again, 1 should not divide by 0. Your range, instead of y cannot equal 0, it is that y cannot equal 2 because it has shifted up. Now, the last one, very similar, except instead of going 2 up, we've gone 2 down. The domain is the same, x does not equal 0. And the range now is that y does not equal -2, and that's all that we need to do for that page. Going to stop it now so that we don't have to spend forever buffering.